Today we are going to see chapter 9 Gravitation. We have learned about the motion of objects and force as the cause of motion. We have learned that a force is needed to change the speed or the direction of motion of an object. We always observe that an object dropped from a height falls towards the earth. We know that all the planets go around the sun, the moon goes around the earth. In all these cases, there must be some force acting on the objects, the planets, and on the moon. Isaac Newton could grasp that the same force is responsible for all these. This force is called the gravitational force. In this chapter, we shall learn about gravitation and the universal law of gravitation. We shall discuss the motion of objects under the influence of gravitational force on the earth. We shall study how the weight of a body varies from place to place. We shall also discuss the conditions for objects to float in liquids. 9.1 Gravitation. We know that the moon goes around the earth. An object, when thrown upwards, reaches a certain height and then falls downwards. It is said that when Newton was sitting under a tree, an apple fell on him. The fall of the apple made Newton start thinking. He thought that if the earth can attract an apple, can it not attract the moon? Is the force the same in both cases? He conjectured that the same type of force is responsible in both the cases. He argued that at each point of its orbit, the moon falls towards the earth instead of going off in a straight line. So it must be attracted by the earth. But we do not really see the moon falling towards the earth. Let us try to understand the motion of the moon by recalling activity 7.11. I think it's not there. Okay, take a piece of thread, tie a small stone at one end, hold the other end of the thread and whirl it around as shown in the figure. Note the motion of the stone. Release the thread. Again, note the direction of motion of the stone. Before the thread is released, the stone moves in a circular path with a certain speed and changes direction at every point. The change in direction involves change in velocity or acceleration. The force that causes this acceleration and keeps the body moving along the circular path is acting towards the center. This force is called the centripetal, meaning center-seeking force. In the absence of this force, the stone flies off along a straight line. The straight line will be a tangent to the circular path. In the figure A, B, C, a straight line that meets the circle at one and only one point is called a tangent to the circle. Straight line ABC is a tangent to the circle at point B. The motion of the moon around the earth is due to the centripetal force. The centripetal force is provided by the force of attraction of the earth. If there were no such force, the moon would pursue a uniform straight line motion. It is seen that a falling apple is attracted towards the earth. Does the apple attract the earth? If so, we do not see the earth moving towards an apple. Why? According to the third law of motion, the apple does attract the earth. But according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object. The mass of an apple is negligibly small compared to that of the earth. So, we do not see the earth moving towards the apple. Extend the same argument for why the earth does not move towards the moon. In our solar system, all the planets go around the sun. By arguing the same way, we can say that there exists a force between the sun and the planets. From the above facts, Newton concluded that not only does the earth attract an apple and the moon, but all objects in the universe attract each other. This force of attraction between objects is called the gravitational force. 9.1.1 Universal law of gravitation. Every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square root of the square of the distance between them. I repeat, every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. The force is along the line joining the centers of two objects. In the figure, the formula is F is equal to G into capital M small m divided by d squared. So let two objects A and B masses m and small m lie at a distance small d from each other as shown in the figure. Let the force of attraction between two objects be F. According to the universal law of gravitation, the force between two objects is directly proportional to the product of their masses. That is, capital M is directly proportional to capital M into small m. And the force between two objects is inversely proportional to the square of the distance between them. That is, F is directly proportional to 1 by small d square. Combining the two equations, we get F is directly proportional to capital M into small m divided by small d squared. Or F is equal to G capital M small m divided by d square, where G is the constant of proportionality and is called the universal gravitation constant. By multiplying crosswise, which gives capital F into d squared is equal to capital G capital M into small m, or the G is equal to capital M d squared divided by capital M and small m. So, the SI unit of G can be obtained by substituting the units of force, distance and mass in the above equation as Newton, meter squared, kilogram, minus 2, power of minus 2. I repeat, Newton, m square, kilogram to the minus 2, kilogram to the power minus 2. The value of G was found out by Henry Cavendish by using a sensitive balance. The accepted value of G is 6.673 into 10 to the power of minus 11 Newton meter squared per kilogram squared. 6.673 into 10 to the power of minus 11 Newton meter squared per kilogram squared. We know that there exists a force of attraction between any two objects. Compute the value of this force between you and your friend sitting close by. Conclude how you can not experience this force. The law is universal in the sense that it is applicable to all bodies, whether the bodies are big or small, whether they are celestial or terrestrial. Inverse square, saying that F is inversely proportional to the square of distance D means, for example, that if D gets bigger by a factor of 6, F becomes 1 by 36 times smaller. Example 9.1. The mass of Earth is 6 into 10 to the power of 24 kilograms and that of the Moon is 7.4 into 10 to the power of 22 kilograms. If the distance between the Earth and the Moon is 3.84 into 10 to the power of 5 kilometers, calculate the force exerted by the Earth on the Moon. Take G is equal to 6.7 into 10 to the power of minus 9 Newton meter squared per kilogram squared. Solution. The mass of the Earth capital M is equal to 6 into 10 to the power of 24 kilograms. The mass of the Moon is equal to small m 7.4 into 10 to the power of 22 kilograms. The distance between the Earth and the Moon D is equal to 3.87 into 10 to the power of 5 kilometers is equal to 3.84 into 10 to the power of 5 into 1000 meters. That gives you 3.84 into 10 to the power of 8 meters. So G is equal to 6.7 into 10 to the power of minus 11 newtons meter squared per kilograms. From the equation above, the force exerted by Earth on the Moon is capital F is equal to capital G, capital M into M divided by D squared. So 6.7 into 10 to the power of 11 Newton meter squared per kilogram squared into 6 into 10 to the power of 24 kilogram into 7.4 into 10 to the power of 22 kilograms divided by 3.84 into 10 to the power of 8 meter whole squared, which gives you 2.02 into 10 to the power of 20 newtons. Thus, the force exerted by Earth on the Moon is 2.02 into 10 to the power of 20 newtons. Importance of the universal law of gravitation. The universal law of gravitation successfully explained in several phenomena which were believed to be unconnected. The force that binds us to the earth, the motion of the moon around the earth, the motion of the planets around the sun, and the tides due to the moon and the sun. I repeat, the importance of the universal law of gravitation. The universal law of gravitation successfully explained several phenomena which were believed to be unconnected. The force that binds us to the earth, the motion of the moon around the earth, the motion of planets around the sun, and the tides due to the moon and the sun. Free fall. Let us try to understand the meaning of free fall by performing this activity. Take a stone, throw it upwards. It reaches a certain height and then it starts falling down. We have learned that the earth attracts objects towards it. This is due to the gravitational force. Whenever objects fall towards the earth under this force alone, we say that the objects are in free fall. Is there any change in the velocity of falling objects? While falling, there is no change in the direction of motion of the objects, but due to the Earth's attraction, there will be a change in the magnitude of the velocity. Any change in velocity involves acceleration. Whenever an object falls towards the Earth, an acceleration is involved. This acceleration is due to the Earth's gravitational force. Therefore, this acceleration is called the acceleration due to the gravitational force of the Earth, or acceleration due to gravity. It is denoted by g. The unit of g, small g, is the same as that of acceleration, that is meter per second squared. We know from the second law of motion that force is the product of mass and acceleration. Let the mass of the stone in the activity 9.2 be small m. We already know that there is acceleration involved in falling objects due to the gravitational force and is denoted by g. Therefore, the magnitude of the gravitational force F, capital F, will be equal to the product of mass and acceleration due to the gravitational force, that is capital M is equal to capital F is equal to small m and small g. From the above equations, we have small m and g is equal to capital G, capital M multiplied by small m divided by d squared, or the small g is equal to capital G, capital M divided by d squared, where the capital M is the mass of the earth and small d is the distance between the object and earth. Let an object be on or near the surface of the earth. The distance d in equation will be equal to r, the radius of the earth. Thus, for an object on or near the surface of the earth is equal to small m, small g is equal to capital G, capital M multiplied by small m divided by capital R squared. So, the small g is equal to capital G, capital M divided by R squared. The earth is not a perfect sphere. As the radius of the earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator. For most calculation, we can take g to be more or less constant on or near the earth, but for objects far from the earth, the acceleration due to the gravitational force of the earth is given by the equation. So 9.2.1, to calculate the value of g. To calculate the value of g, we should put the values of capital G, capital M and R in equation, namely universal gravitational constant, capital G is equal to 6.7 into 10 to the minus 11 newtons meter squared per kg squared. Mass of the earth m is equal to 6 into 10 to the power of 24 kilograms, and radius of the earth capital R is equal to 6.4 into 10 to the power of 6 meter. So the G, gravitational force, is equal to capital G capital M divided by R squared, which gives you 9.8 meter per second squared. Thus, the value of acceleration due to gravity of the earth G is equal to 9.8 meter per squared. Motion of objects under the influence of gravitational force of the earth. Let us do an activity to understand whether all objects, hollow or solid, big or small, will fall from a height at the same rate. Take a sheet of a paper and a stone and drop them simultaneously from the first floor of a building. Observe whether both of them reach the ground simultaneously. We see that the paper reaches ground a little later than the stone. This happens because of air resistance. The air offers resistance due to friction to the motion of the falling objects. The resistance offered by air to the paper is more than the resistance offered to the stone. If we do the experiment in glass jar from which air has been sucked out, the paper and the stone would fall at the same rate. We know that an object experiences acceleration during free fall. From equation, this acceleration experienced by an object is independent of its mass. This means that all objects, hollow or solid, big or small, should fall at the same rate. According to a story, Galileo dropped different objects from the top of the Leaning Tower of Pisa in Italy to prove the same. As G is constant near the Earth, all the equations for the uniformly accelerated motion of an object become valid with acceleration A replaced by G. The equations are V is equal to U plus AT, S is equal to UT plus of AT squared, V squared is equal to U squared plus 2AS, where U and V are the initial and final velocities and S is the distance covered in time t. In applying these equations, we will take acceleration A to be positive when it is in the direction of the velocity, that is, in the direction of motion. The acceleration A will be taken as negative when it opposes the motion.